Close your eyes for a moment. I want you to imagine a sound you've never truly heard. Not the gentle hum of a city or the whisper of the wind through familiar trees, but a sound from a forgotten world. A deep, resonant bellow that shakes the very ground beneath your feet. A noise so powerful it feels less like hearing and more like a physical force. It's the sound of a lung the size of a small car exhaling, the vibration of vocal cords thicker than a ship's mooring rope. It's a sound that hasn't echoed across this planet in 66 million years. Now, open your eyes. That world, that lost empire of life, is where we're going today. This isn't just a story about bones and fossils. It's an exploration of a planet you would barely recognize, ruled by creatures more fantastic than any myth or legend. We are about to unlock 100 of its most incredible, mind-bending, and altogether amazing secrets. Let's begin with the most fundamental concept of all: time. The entire reign of the non-avian dinosaurs, the so-called Mesozoic Era, lasted for a staggering 180 million years. To try and wrap your head around that number is almost impossible. The entire recorded history of humanity, from the first cuneiform scripts etched into clay tablets to the digital world you're living in right now, is a mere 5,000 years. The entire existence of our species, Homo sapiens, is perhaps 300,000 years. You could fit the whole of human existence into the age of dinosaurs 600 times over, with room to spare. They weren't a brief chapter in Earth's history, they were the book. This immense passage of time means that the dinosaurs we often picture together in our minds were, in reality, separated by gulfs of time larger than the one that separates us from them. The famous Stegosaurus, with its iconic backplates and spiked tail, was already a fossil, already buried deep in the ground for 80 million years before the first Tyrannosaurus rex ever hatched. That time gap is greater than the 66 million years that lie between the last T-Rex and you. We think of the Jurassic and the Cretaceous as one big dinosaur party, but in reality, they were distinct epochs, different worlds with their own unique casts of characters. A planetary dynasty that rose, flourished, and fell in countless iterations, long before our own story even had a preface. And while their reign was long, the name we use for them is surprisingly recent. The word dinosaur itself, which seems so ancient and primal, was only coined in 1842 by the English paleontologist Sir Richard Owen. It's a combination of the Greek words dinos, meaning terrible or fearfully great, and sauros, meaning lizard. So dinosaur literally translates to terrible lizard. Owen chose this name when he realized that the fossil remains of Megalosaurus, Iguanodon, and Hylaeosaurus belonged to a completely new and distinct group of reptiles, unlike anything known to science at the time. He saw in their massive bones and powerful builds a creature that was fearfully great, a testament to a lost world of giants. It's a name that has stuck, capturing the public imagination for nearly 2 centuries, even though we now know they were far more complex and diverse than just simple, terrible lizards. In fact, many were not terrible at all, and a huge number weren't even particularly lizard-like. But the power of that name, that initial impression of awe and terror, has defined them ever since. For all the talk of terrible lizards, not all of them were giants. While we are captivated by the colossal sauropods and the ferocious tyrannosaurs, the Mesozoic world was also filled with dinosaurs that were surprisingly small. One of the smallest known was Compsognathus, a theropod from the late Jurassic period. It was no bigger than a modern-day chicken, weighing only about 3 kilograms, or around 7 pounds. Its delicate, hollow bones and lightweight frame made it a swift and agile hunter, likely preying on small lizards, insects, and other tiny creatures. Fossils of Compsognathus have even been found with the remains of its last meals preserved inside its rib cage, giving us a direct window into its diet. It's a powerful reminder that the dinosaur ecosystem was just as varied as our own. For every elephant, there's a mouse. For every blue whale, a minnow. The world of dinosaurs had its own tiny players, scurrying through the undergrowth of giant ferns, living lives just as dramatic and perilous as their enormous cousins, a world teeming with life at every conceivable scale. Imagine a creature that looks like a vicious predator, but is in reality a feathered, bird-like animal, darting through the prehistoric landscape, a tiny terror in a world of giants. Its existence a crucial piece in the puzzle of how these magnificent animals evolved. On the absolute other end of that scale, we find the true titans, the largest animals ever to walk the earth. The title of biggest dinosaur is a hotly contested one, as complete skeletons of these giants are incredibly rare. However, the current heavyweight champion is generally considered to be Argentinosaurus. This titanosaurian sauropod, which lived in what is now Argentina during the late Cretaceous, was a creature of almost unbelievable proportions. Estimates based on its colossal vertebrae, some of which are taller than a full-grown man, and its 5-foot-wide femur suggest a length of up to 130 feet or 40 meters and a weight approaching 100 tons. That's the equivalent of a dozen elephants combined. Imagine an animal so massive that each footfall would have sent tremors through the ground. A walking mountain of flesh and bone that would have had to consume hundreds of pounds of vegetation every single day just to sustain itself. Its neck was so long it could have grazed from treetops several stories high, and its heart would have needed to be the size of a small car, pumping blood with immense pressure to reach its distant brain. These weren't just animals, they were living, breathing ecosystems, their sheer scale warping the world around them, their presence defining the very landscape they inhabited. Their existence pushes the boundaries of what we thought was biologically possible for a land animal. The sheer diversity in size is just the beginning. The variety of dinosaur shapes and forms is mind-boggling, and some of them were truly bizarre. Take Carnotaurus, for instance. Its name means meat-eating bull, and for good reason. This late Cretaceous predator from South America had two prominent, sharp horns growing out of its skull, just above its eyes, a feature completely unique among large theropods. No one is entirely sure what they were for. Were they used for combat with rivals, for display to attract mates, or perhaps even for ramming prey? Its skull was also unusually short and deep, and its eyes faced almost directly forward, giving it excellent binocular vision, a key trait for a predator needing to judge distances accurately. But the strangest thing about Carnotaurus wasn't its horns, it was its arms. They were absolutely minuscule, even smaller in proportion than those of a T-Rex. They were so reduced that the forearm was basically just a wrist stump with 4 tiny, non-functional fingers. These were arms that could not have possibly reached its mouth or been used for grasping. It was a predator that relied entirely on the speed of its long legs and the power of its gaping jaws. A truly unique and specialized hunter that looks like something cobbled together from a strange evolutionary dream. And speaking of dreams, or perhaps nightmares, let's talk about teeth. The famous Tyrannosaurus rex didn't just have big teeth, it had the largest teeth of any known carnivorous dinosaur. The biggest T-Rex tooth ever found measured a staggering 12 inches or 30 centimeters long from root to tip. That's the length of a dinner plate. But it wasn't just the size that made them so formidable, it was their shape. Unlike the blade-like slicing teeth of many other theropods, a T-Rex's tooth was thick, rounded and robust, more like a railroad spike than a knife. This design, combined with its immense jaw strength, meant its teeth weren't just for slicing flesh. They were for crushing bone. They were biological bone crushers. Paleontologists have found Triceratops bones with deep puncture wounds and scrapes that perfectly match the size and spacing of T-Rex teeth, evidence of a bite so powerful it could shatter the skeletons of its prey. This allowed T-Rex to access the nutrient-rich marrow inside the bones, a food source unavailable to many of its competitors. It wasn't just a hunter, it was a living can opener for other giant dinosaurs. The power behind that bite was truly immense. Modern biomechanical studies, using computer models based on the T-Rex's skull structure and muscle attachment points, have estimated its bite force to be somewhere between 8,000 and 12,800 pounds per square inch. To put that in perspective, a lion, one of today's most powerful predators, has a bite force of about 1,000 psi. A great white shark is around 4,000 psi. The T-Rex could bite down with a force 3 times greater than a great white shark and more than 10 times that of a lion. It was a bite that could literally pulverize bone, shearing through the thick armor and skeletons of its prey with terrifying ease. This wasn't a delicate nip, it was an explosion of force. Imagine the sound of it, not a clean slice, but a sickening crunch, like a building being demolished as tons of pressure were brought to bear on a single point. This incredible power allowed T-Rex to take down some of the most heavily armed and armored herbivores of its time, making it the undisputed apex predator of its environment. Of course, T-Rex wasn't the only dinosaur with incredible headgear. The award for the longest horns of any known animal goes to Triceratops. Its name literally means three-horned face, and its iconic skull sported 2 massive brow horns above its eyes and a smaller horn on its nose. The 2 main horns could grow to be over 3 feet or 1 meter long. These weren't just for show. They were formidable weapons made of a solid bone core covered in a sheath of keratin, the same material that makes up our fingernails and the horns of a bull. These horns, combined with the solid shield of bone at the back of its skull called a frill, made Triceratops a very dangerous animal to attack. The fossil record bears this out. Paleontologists have found T-Rex bones with healed puncture wounds that perfectly match the shape and size of a Triceratops horn, evidence that these herbivores fought back, and sometimes they won. It was a true clash of the titans, the ultimate bite force versus the ultimate defensive weaponry, a prehistoric arms race played out on the plains of ancient North America. But what about the dinosaurs that relied on armor instead of horns? Enter Ankylosaurus, the living tank of the Cretaceous period. This dinosaur was covered from head to tail in thick, bony plates called osteoderms, creating a near impenetrable suit of armor. Even its eyelids were made of bone. It was low to the ground, built like a fortress, making it incredibly difficult for a predator like T-Rex to flip it over and attack its soft underbelly. But its most famous feature was at the other end of its body, a massive bony club at the end of its tail. This club was formed by several large osteoderms fused together with the last few tail vertebrae, creating a heavy, solid sledgehammer. Powerful muscles at the base of the tail could swing this club with devastating force, enough to shatter the leg bones of an attacking Tyrannosaurus. Finding an Ankylosaurus fossil with a perfectly preserved tail club is a paleontological treasure, a direct piece of evidence for one of the most effective and incredible defensive weapons ever evolved. It was a walking fortress with a wrecking ball for a tail. Not all defenses were so aggressive. Some dinosaurs may have used camouflage to avoid being detected in the first place. For a long time, figuring out the color of dinosaurs was thought to be impossible. We had the bones, but the soft tissues, the skin and feathers were gone. But in recent years, incredible scientific breakthroughs have changed everything. By studying fossilized skin impressions and, even more amazingly, by analyzing microscopic structures called melanosomes preserved in fossilized feathers, scientists can now determine the actual colors and patterns of some dinosaurs. One of the most beautifully preserved examples is a dinosaur called Borrielopelta, an armored nodosaur discovered in a Canadian mine. It was so perfectly preserved that it looks more like a statue than a fossil, with its armor plates and skin intact. Analysis of its skin pigments revealed it likely had a reddish-brown color and employed a form of countershading, with a darker back and a lighter underside. This is a common camouflage pattern in modern animals, helping them to blend in with their environment and avoid predators. So far from being drab gray or green creatures, we now have hard evidence that at least some dinosaurs were intricately patterned and colored, masters of disguise in a dangerous world. The world they lived in was also fundamentally different from our own. During much of the Mesozoic era, the continents were not in their current positions. They were clumped together in a massive supercontinent known as Pangaea. This single landmass meant that, in theory, a dinosaur could have walked from what is now the South Pole all the way to the North Pole. Pangaea began to break apart during the Triassic and Jurassic periods, a slow, epic continental drift that created new oceans and separated dinosaur populations. This geological drama had a profound impact on their evolution. As continents drifted apart, dinosaur communities became isolated from each other, leading them to evolve in unique ways, adapting to their new, specific environments. This is why we find certain families of dinosaurs, like the horned ceratopsians and the tyrannosaurs, primarily in North America and Asia, which were connected for a time, while others, like the strange horned Carnotaurus, are found in the southern continents of Gondwana. The story of the dinosaurs is inextricably linked to the story of our planet's shifting crust, a tale of evolution driven by the slow, inexorable dance of the continents. The atmosphere they breathed was different too. For significant portions of the Mesozoic, the level of oxygen in the atmosphere was much higher than the 21% we have today, possibly reaching as high as 30 to 35%. This oxygen-rich air would have had a number of fascinating effects. For one, it would have made wildfires much more frequent and intense, a constant danger in the prehistoric forests. But it also may have been one of the keys to the dinosaurs' success, particularly the giant sauropods. Higher oxygen levels would have supported a more energetic metabolism, potentially allowing these colossal animals to grow to their immense sizes and power their massive bodies. It's a tantalizing idea that the very air they breathed was a supercharged fuel that enabled the evolution of the largest land animals in history. It also means that if you were to travel back in time, the air itself would feel different, thicker, and more potent, a heady cocktail that fueled a world of giants. And those giants grew at an incredible rate. We know this by studying the internal structure of their bones. Just like trees, dinosaur bones have growth rings. By slicing a fossilized bone into a thin section and examining it under a microscope, paleontologists can count these rings to determine the dinosaur's age when it died. But more than that, the spacing of the rings reveals how fast it was growing. Wide rings mean rapid growth, while narrow rings indicate slower growth. What these studies have shown is astonishing. A huge sauropod like Argentinosaurus, which hatched from an egg no bigger than a football, reached its colossal adult size in just 20 to 30 years. To do this, it would have had to pack on pounds every single day of its young life. This incredibly rapid growth rate is more similar to that of birds and mammals than to modern reptiles, which grow slowly throughout their lives. This leads us to one of the most significant shifts in our understanding of dinosaurs. They were not the slow, sluggish, cold-blooded creatures we once thought. This brings us to the great warm-blooded versus cold-blooded debate. For decades, dinosaurs were depicted as classic reptiles, basking in the sun to warm up and becoming sluggish at night. But the evidence, like those rapid growth rates, points to something different. Many paleontologists now believe that most dinosaurs, especially the active predatory theropods and the giant sauropods, had a metabolically active, warm-blooded physiology, more akin to modern birds and mammals. This is known as endothermy. A warm-blooded metabolism would have been necessary to sustain the active lifestyles of hunters like Velociraptor, or to fuel the non-stop eating and growing of a young Apatosaurus. Their bone structure, which is filled with blood vessels in a pattern similar to mammals, also supports this idea. They were dynamic, energetic animals with a high metabolism that powered their incredible lives. This completely revolutionizes our image of them, transforming them from lumbering lizards into vibrant, active creatures that truly dominated their world. The discovery of dinosaur nests and eggs has given us an unprecedented look into their family lives. One of the most famous sites is in Montana, nicknamed Egg Mountain, where paleontologists found the nesting grounds of a duck-billed dinosaur called Maiasaura. Its name, in fact, means good mother lizard. The discovery was revolutionary because it showed dinosaurs weren't just egg layers, they were caring parents. The nests were built in colonies, spaced about one adult body length apart, suggesting they were social animals. Inside the nests, they found the remains of baby Maiasaura with underdeveloped leg joints, indicating they were unable to walk immediately after hatching and would have been dependent on their parents for food and protection. This was the first solid proof of parental care in dinosaurs. It paints a beautiful picture of these giant creatures gently tending to their young, bringing back vegetation for them to eat, and standing guard against predators, a testament to the complex social behaviors that existed in the Mesozoic world. And dinosaur eggs came in all shapes and sizes. The largest dinosaur eggs ever found belonged to a type of giant oviraptorosaur from China and measured up to 2 feet in length. They were elongated, almost like giant torpedoes. On the other end of the spectrum, the smallest eggs are just a few centimeters across. Interestingly, even the largest dinosaurs, the 100-ton sauropods, laid relatively small eggs, usually no bigger than a soccer ball. This was likely due to physical constraints. An egg needs to be porous enough to allow oxygen to reach the embryo. But if it gets too large, the shell has to become so thick to support its own weight that it would suffocate the embryo inside. This meant that even the most colossal dinosaur began its life as a tiny, vulnerable hatchling, facing a world of predators and challenges, its survival depending on its ability to grow at that explosive rate we talked about earlier. One of the most touching fossil discoveries ever made seems to show a dinosaur in the act of brooding on its nest, just like a modern bird. A fossil of a small theropod called Oviraptor was found in Mongolia, positioned directly over a clutch of eggs. Initially, paleontologists thought it was an egg thief, hence the name Oviraptor, which means egg seizer. They assumed it had died while raiding another dinosaur's nest. But decades later, new discoveries of similar fossils and a closer examination of the embryo inside one of the eggs revealed the truth. The eggs belonged to the Oviraptor itself. It wasn't stealing the eggs, it was protecting them. It was a parent shielding its young with its own body, and it died in that protective pose, likely buried by a sudden sandstorm. This discovery completely redeemed Oviraptor's reputation, transforming it from a villain into a devoted parent and providing some of the strongest evidence for the intimate connection between dinosaurs and their modern descendants, birds. That's right, birds are dinosaurs. This is no longer a fringe theory, it's a scientific consensus. Birds are the direct descendants of a group of small, feathered theropod dinosaurs. The fossil evidence for this is overwhelming, from shared skeletal features like a wishbone and hollow bones to the presence of feathers on a huge number of non-avian dinosaur fossils. Think of it this way: saying birds aren't dinosaurs is like saying humans aren't mammals. They are a branch of the dinosaur family tree that survived the extinction event and continued to evolve into the 10,000+ species we see today. So, when you see a pigeon on the street or a hummingbird in your garden, you are looking at a living, breathing dinosaur. The age of dinosaurs never truly ended, it just learned to fly. The poster child for this transition is, of course, Archaeopteryx. Discovered in Germany in the 1860s, this fossil was a stunning missing link that showed a perfect blend of dinosaur and bird features. It had flight feathers and wings just like a modern bird, but it also had a jaw full of sharp teeth, a long bony tail, and claws on its wings, all classic reptilian, or rather dinosaurian traits. For over a century, it was the definitive proof of the evolutionary link. For a long time, scientists debated whether it could truly fly or if it was just a glider. Recent studies of its bone structure and feather arrangement suggest it was capable of active, flapping flight, though perhaps not with the same power and agility as modern birds. It was a pioneer of the skies, a creature of two worlds, beautifully capturing a pivotal moment in evolutionary history. But Archaeopteryx wasn't alone. We now know that feathers were widespread among theropod dinosaurs, and they didn't evolve for flight, at least not initially. The first feathers were likely simple, hair-like filaments, probably used for insulation to help these active, warm-blooded animals regulate their body temperature. We've found fossils of dinosaurs like Sinosauropteryx covered in this downy, proto-feather fuzz. Over millions of years, these simple structures evolved into more complex, branching feathers. These might have been used for display, with bright colors and patterns to attract mates or intimidate rivals, much like a peacock's tail today. Only later, in certain lineages, were these already complex feathers co-opted for an entirely new purpose: flight. This is a classic example of exaptation in evolution, where a trait that evolved for one purpose is later used for something completely different. Some of these feathered dinosaurs were truly spectacular. Consider Yutyrannus, a relative of T-Rex discovered in China. This was a large predator, about 30 feet long, and its fossils were found with clear impressions of long, shaggy, filamentous feathers covering its body. This discovery was a game-changer. It proved that even large tyrannosauroids had feathers, suggesting that perhaps even the mighty T-Rex itself had some form of feathering, at least when it was young. It conjures up a whole new image of these iconic predators, not as scaly monsters, but as giant, fluffy, bird-like beasts. The line between what we call a dinosaur and what we call a bird becomes blurrier and more beautiful with every new discovery. And some feathered dinosaurs had not 2 wings, but 4. A fascinating group of small raptor-like dinosaurs, including the famous Microraptor, had long aerodynamic feathers not just on their arms, but on their legs as well, creating a biplane-like configuration. Scans of Microraptor fossils have even revealed the color of its feathers. They were black and iridescent with a glossy sheen like a modern-day crow or starling. It likely used its 4 wings to glide or fly from tree to tree in the ancient forests of China. It's a stunning example of the incredible evolutionary experimentation that was happening during the Mesozoic, a time when nature was trying out all sorts of weird and wonderful ways to conquer the skies. Let's return to the ground for a moment and talk about intelligence. How smart were dinosaurs? It's a difficult question to answer with certainty, but we can get clues from their brain size relative to their body size, a measure known as the encephalization quotient, or EQ. By creating digital endocasts of the inside of their skulls, scientists can map the shape and size of their brains. What they've found is a huge range. A dinosaur like Stegosaurus, for example, was famously thought to have a brain the size of a walnut. While it was a bit larger than that, about the size of a lime, its EQ was extremely low. It was a slow-moving, heavily armored herbivore whose life didn't require complex problem-solving. It was likely operating mostly on instinct. At the other end of the spectrum were the dromaeosaurs, the group that includes Velociraptor. These dinosaurs had some of the largest brains relative to their body size of any non-avian dinosaur. Their EQs were comparable to those of modern ostriches or emus, which are not known for being geniuses, but are certainly capable of complex behaviors. The parts of their brains associated with sight and processing were particularly large, indicating they were visually oriented predators with sharp senses. While they probably weren't the hyper-intelligent, door-opening pack hunters depicted in movies, they were certainly among the cleverest dinosaurs of their time, quick, adaptable predators that used their intelligence to survive. Speaking of Velociraptor, the creature we see in popular culture is vastly different from the real animal. The movie version is depicted as a 6-foot-tall, scaly creature. The real Velociraptor, which lived in the deserts of Mongolia, was actually about the size of a turkey, standing only about 1.5 feet tall at the hip. And, as a dromaeosaur, it would have been covered in feathers. But its most famous feature, the sickle-shaped claw on the second toe of each foot, was very real. This claw was held retracted while walking, keeping it razor-sharp. It wasn't used for disemboweling prey, as is often shown. Instead, studies of its anatomy and comparisons with modern birds of prey suggest it was used as a climbing tool to latch on to the sides of struggling prey, using its wings for balance while it pinned the victim down and began to eat, a behavior known as raptor prey restraint. It was a small, feathered, but undeniably fierce predator. The name of the dinosaur Utahraptor corrects the size issue. Discovered in Utah, this dromaeosaur was a true giant of its kind. It lived millions of years before Velociraptor and was a much more formidable animal, reaching lengths of up to 20 feet and weighing over 1,000 pounds. It was the raptor of Hollywood nightmares made real. It had the same sickle claw as its smaller cousins, but on a much larger scale, a terrifying weapon 9 inches long. A pack of these creatures would have been capable of taking down prey many times their own size, a truly frightening prospect in the early Cretaceous. Many dinosaurs were highly social animals. Fossil trackways provide some of the most compelling evidence for this. In various locations around the world, paleontologists have found sites with dozens or even hundreds of dinosaur footprints, all heading in the same direction, preserved in ancient mud. There are trackways of giant sauropods that show a herd structure, with the large adults on the outside and the smaller, younger individuals in the middle, presumably for protection. There are also trackways of duck-billed hadrosaurs and horned ceratopsians, suggesting they traveled in vast herds, much like the bison of North America or the wild beast of Africa. These silent stone footprints tell a dynamic story of migration, family, and community. Some dinosaurs even had elaborate structures for communication. The duck-billed hadrosaurs, also known as the cows of the Cretaceous, are famous for the bizarre crests on their heads. Dinosaurs like Parasaurolophus had a long, hollow, tube-like crest extending from the back of its skull. For a long time, its function was a mystery. Theories ranged from it being a snorkel to a weapon. But by using CT scans to map the internal structure of the crest, scientists discovered it contained a complex series of nasal passages. By blowing air through these passages, Parasaurolophus could have produced deep, resonant, trombone-like calls that would have carried for miles. Each species of hadrosaur had a uniquely shaped crest, meaning each would have produced a different sound. These crests were likely used for communication within the herd, to signal danger, for species recognition, or to call for mates, filling the Cretaceous air with a symphony of strange and wonderful sounds. Not all dinosaur sounds were vocal. Some may have communicated through infrasound, sounds too low for the human ear to hear. Modern elephants use infrasound to communicate over long distances. The massive nasal cavities of some large dinosaurs, like the sauropods, may have acted as resonance chambers for producing these low-frequency rumbles. These vibrations would have traveled through the ground as well as the air, allowing these giant animals to stay in contact with each other even when they were out of sight, sending messages across the vast prehistoric landscapes. It's a fascinating thought that the world of the dinosaurs was filled not only with roars and calls we could have heard, but also with a silent, secret language of vibrations shaking the very earth. Let's dig into their diet. How do we know what they ate? The most obvious clue is their teeth. The sharp, serrated teeth of a T-Rex are clearly for meat, while the flat, grinding teeth of a Triceratops are built for shredding tough plant material. But we have even more direct evidence: fossilized stomach contents. The beautifully preserved Boreopelta, the armored nodosaur, had its last meal preserved in its stomach. Analysis revealed it was a very picky eater, primarily consuming specific types of ferns, ignoring the more common cycads and conifers around it. This gives us an incredibly detailed snapshot of its diet and feeding behavior. And then there's the less glamorous, but equally informative evidence: fossilized dinosaur droppings known as coprolites. These might not be the most exciting fossils to find, but they are a treasure trove of information. By slicing them open and analyzing their contents, scientists can identify pollen, fragments of plants, and even bits of bone, revealing precisely what a dinosaur was eating. Some coprolites attributed to Tyrannosaurus have been found containing the crushed-up bones of a young herbivore, confirming its bone-crunching feeding style. Coprolites are a direct, unfiltered window into the prehistoric food web. Some dinosaurs had truly strange eating habits. Spinosaurus is one of the most enigmatic and bizarre dinosaurs ever discovered. Originally found in Egypt over a century ago, the original fossils were destroyed in a bombing raid during World War II. But recent discoveries of new skeletons in Morocco have revealed a creature stranger than anyone imagined. It had a huge sail on its back, a long, crocodile-like snout filled with conical teeth, and a paddle-like tail. Its dense bones and the chemical isotopes in its teeth suggest it was a semi-aquatic animal, spending much of its life in and around water. It was likely a river monster, the largest carnivorous dinosaur known, even larger than T-Rex. And it probably hunted giant fish, crocodiles, and anything else it could snatch from the riverbanks. It was a dinosaur that had adapted to a niche unlike any other, a prehistoric combination of a crocodile, a heron, and a whale. And then there's Therizinosaurus, perhaps the weirdest dinosaur of all. When its fossils were first found, paleontologists were completely baffled. They found enormous sickle-like claws that were nearly a meter long. They naturally assumed they belonged to a terrifying predator. But when more of the skeleton was discovered, it revealed a creature with a small skull, a long neck, and a pot-bellied body, all features of an herbivore. It turns out Therizinosaurus was a plant eater. So what were those gigantic claws for? The leading theory is that they were used as giant rakes to pull down high branches to its mouth, or perhaps for defense against predators like Tarbosaurus, a close relative of T-Rex. It was a walking paradox, a sloth-like herbivore armed with the most fearsome-looking claws in the animal kingdom. Dinosaurs inhabited every continent on Earth, including Antarctica. During the Mesozoic Era, Antarctica was not the frozen wasteland it is today. It was located further north, was part of the supercontinent Gondwana, and had a much milder climate, supporting vast temperate forests. Dinosaurs like the herbivore Antarctopelta and the predator Cryolophosaurus roamed these forests. Cryolophosaurus is particularly interesting. It had a strange, forward-curving crest on its head, earning it the nickname Elvosaurus. Living in Antarctica, even a milder version, would have meant dealing with months of total darkness during the winter. This suggests that these polar dinosaurs were adapted to survive in low-light conditions, perhaps having large eyes or other specialized senses. We can estimate the speed of dinosaurs from their fossilized trackways. By measuring the distance between footprints, the stride length, the size of the foot, and estimating the animal's leg length, scientists can use a formula to calculate how fast it was moving. The results show a wide range of speeds. Large sauropods were walkers, moving at a placid 2 to 5 miles per hour. A fast-moving T-Rex could likely manage speeds of around 15 to 25 miles per hour, fast enough to catch most of its prey, but probably not the jeep-chasing sprints seen in movies. The speed champions were likely the ostrich-like ornithomimids, such as Struthiomimus. With their long legs and lightweight bodies, they could have reached speeds of 40 to 50 miles per hour, making them some of the fastest animals of their time. The lifespan of a dinosaur is another area we can investigate through its bones. Those same growth rings that tell us how fast they grew can also tell us how long they lived. By counting the rings, we can estimate their age at death. The data suggests that large theropods like T-Rex lived relatively short, fast lives, reaching maturity in their late teens and rarely living past the age of 30. Life as an apex predator was clearly tough and full of risk. In contrast, the giant sauropods, with fewer natural predators once they reached their adult size, likely had much longer lifespans, perhaps living for 60, 80, or even 100 years. Their long lives playing out in slow motion compared to the frantic pace of the predators that hunted their young. The iconic plates of Stegosaurus have been a source of debate for over a century. Were they for defense? It's unlikely. The plates were thin, full of blood vessels, and not very strong, so they would have offered little protection against the bite of a predator like Allosaurus. A more likely theory is that they were used for thermoregulation. The plates had a network of blood vessels running through them. By pumping blood into the plates and turning them towards or away from the sun, Stegosaurus could have absorbed heat or cooled down, acting like giant radiators. Another popular theory is that they were for display, perhaps flushed with color to attract mates or intimidate rivals. It's very possible they served both functions, a multi-purpose biological billboard. The spikes on its tail, however, were a different story. This weapon, technically called a thagomizer, was definitely for defense. The name thagomizer actually comes from a Far Side cartoon by Gary Larson, where a caveman points to a diagram of the spikes and says they are named after the late Thag Simmons. Paleontologists found the name so fitting and funny that it has become the informal but widely used scientific term. And we have proof it was used. An Allosaurus vertebra has been found with a puncture wound that perfectly matches the size and shape of a Stegosaurus tail spike, a fossilized snapshot of a life or death battle. Dinosaurs suffered from diseases and injuries just like modern animals. The study of these conditions in the fossil record is called paleopathology. We have found dinosaur bones with evidence of broken and healed limbs, severe arthritis, bone cancer, osteosarcoma, and infections that left visible marks on the skeleton. One famous T-Rex specimen, nicknamed Sue, has a number of pathologies, including a healed broken leg, damaged ribs, and holes in its jaw that may have been caused by a parasitic infection similar to one that affects modern birds. These fossilized ailments give us a glimpse into the individual lives and struggles of these animals, reminding us that they were not abstract monsters, but living creatures that felt pain and endured hardship. Some dinosaurs replaced their teeth continuously throughout their lives. Sauropods and hadrosaurs, the great plant eaters, were constantly grinding down their teeth on tough vegetation. To cope with this, they had a dental battery system. Instead of a single row of teeth, they had hundreds of teeth packed together in columns, with new teeth constantly growing up from below to replace the ones that wore out. A single Triceratops could have had up to 800 teeth in its mouth at any one time, though only a fraction were in use on the chewing surface. A shark is the best modern analog. This constant supply of fresh, sharp teeth was a key adaptation that allowed them to process enormous quantities of food. The longest dinosaur name belongs to Micropachycephalosaurus, which means tiny, thick-headed lizard. Ironically, despite its incredibly long name, the dinosaur itself was one of the smallest known, measuring only about 3 feet in length. Its name is a perfect example of the descriptive and sometimes unwieldy nature of scientific nomenclature, which relies on Greek and Latin roots to describe the key features of the animal. Dinosaurs may have had a very different kind of vision from us. The position of their eye sockets on their skull gives us a clue. Predators like T-Rex and Velociraptor had forward-facing eyes, giving them excellent binocular vision and depth perception, crucial for hunting. Herbivores, on the other hand, like Triceratops and the hadrosaurs, had eyes positioned on the sides of their heads. This gave them a wide, panoramic field of view, allowing them to watch for danger from almost any direction, but with a blind spot directly in front of them. This is a classic predator-prey adaptation that we see in the animal kingdom today. The sense of smell was also highly developed in some species. By creating endocasts of their brain cases, we can see the size of the olfactory bulbs, the part of the brain that processes smells. Tyrannosaurus rex had enormous olfactory bulbs, suggesting it had a sense of smell comparable to a modern vulture. This has led to a debate about whether T-Rex was primarily a predator or a scavenger. A powerful sense of smell would have been useful for both, either for tracking down living prey or for locating carcasses from miles away. Most likely, it was an opportunist, like most large carnivores today, hunting when it could and scavenging when it had the chance. The giant sauropods faced a unique engineering problem: how to support their immense weight. Their legs were not just massive pillars of bone, they were marvels of biological engineering. Their vertebrae were also incredibly complex. To save weight, they were filled with air sacs, a feature called pneumaticity. These air sacs, which were connected to their respiratory system, made the bones incredibly light for their size without sacrificing strength, creating a structure that was like a biological version of a lattice girder bridge. This is the same adaptation that allows modern birds to have lightweight skeletons for flight, and it's one of the strongest pieces of evidence linking sauropods and birds. Without these hollowed-out, air-filled bones, the giant sauropods would have been too heavy to even move. These air sacs also mean that dinosaurs breathed in a way that was far more efficient than how we mammals breathe. They likely had a bird-like respiratory system, where air flows in a one-way loop through the lungs rather than the in and out tidal breathing of mammals. This system allows for a much more efficient extraction of oxygen from the air. This super efficient breathing would have been essential for powering the high metabolism of active dinosaurs and for fueling the enormous bodies of the sauropods. It's yet another piece of the puzzle explaining how these animals could achieve such incredible sizes and dominate their ecosystems for so long. Dinosaurs might have swallowed stones to help with digestion. These stones, called gastroliths, are found in the stomach region of some dinosaur skeletons, particularly herbivores like the sauropods. The idea is that these dinosaurs, which couldn't chew their food effectively, would swallow rocks that would then get churned around in a muscular gizzard, helping to grind up tough plant material like cycads and ferns. Many modern birds, like chickens and ostriches, do the exact same thing today, swallowing grit to help process their food. Finding a pile of smooth, polished stones alongside a dinosaur skeleton is strong evidence for this fascinating digestive strategy. There's a group of dinosaurs known as the pachycephalosaurs, or thick-headed lizards. These bipedal herbivores are famous for their incredibly thick, dome-shaped skulls. The skull roof of a Pachycephalosaurus could be up to 10 inches thick, made of solid, dense bone. For years, the prevailing theory was that they used these reinforced skulls as battering rams, engaging in head-butting contests for dominance or mates, much like modern bighorn sheep. While this is a compelling image, some recent studies have cast doubt on it, suggesting the bone structure wasn't ideal for absorbing high-impact collisions, and that the domes might have been more for display or flank butting. The debate continues, but their unique skulls make them one of the most recognizable and intriguing dinosaur groups. The largest land predator of all time might not have been T-Rex, but Spinosaurus. Based on the new fossil discoveries, estimates for Spinosaurus now put its total length at over 50 feet, significantly longer than the largest known T-Rex. However, it was likely lighter and more slenderly built than the bulky Tyrannosaurus. They occupied very different ecological niches. T-Rex was a terrestrial hunter of giant herbivores, while Spinosaurus was a semi-aquatic piscivore, a hunter of the great rivers. So while Spinosaurus was the longest, T-Rex was likely the heaviest and most powerful land-based predator. It's a classic case of it depends on how you measure it. Not all dinosaurs fall neatly into the categories of herbivore or carnivore. Some were likely omnivores, eating both plants and animals. The oviraptorosaurs, for example, had strange, toothless beaks. While their name suggests they ate eggs, their diet was likely much more varied. Their powerful beaks could have been used to crush hard-shelled fruits, seeds, mollusks, or even small vertebrates. They were probably generalists, opportunists who ate whatever they could find, a successful strategy in any ecosystem. The distinction between dinosaurs is based on their hips. The two major groups of dinosaurs are the Saurischia, lizard-hipped, and the Ornithischia, bird-hipped. The Saurischeans, which include the two-legged theropods like T-Rex and the long-necked sauropods, have a pelvic structure similar to that of modern lizards, with the pubis bone pointing forward. The Ornithischians, which include armored dinosaurs like Stegosaurus, horned dinosaurs like Triceratops, and the duck-billed hadrosaurs, have a pelvic structure where the pubis bone points backward, parallel to the ischium, similar to the hips of modern birds. This is one of the great ironies of paleontology. Birds, which are literally bird-hipped, actually evolved from the lizard-hipped Saurischian dinosaurs, not the Ornithischians. Evolution is full of these strange twists and turns. The world the dinosaurs lived in was, for the most part, a greenhouse world. There were no polar ice caps, and sea levels were much higher than they are today. Large parts of the continents were flooded by shallow inland seas. The climate was generally warmer and more humid, with less variation between the poles and the equator. This warm, stable climate allowed for lush vegetation to grow all over the world, providing the enormous food base needed to support the giant herbivorous dinosaurs and, in turn, the carnivores that preyed on them. Fossilized skin impressions are incredibly rare, but they give us a fantastic idea of what dinosaur skin looked like. For most dinosaurs, it wasn't scaly in the way a modern snake or lizard is, with overlapping scales. Instead, it was composed of a mosaic of non-overlapping, bumpy scales called tubercles, a bit like the skin of a crocodile or the pebbly skin on the foot of a chicken. These skin impressions come from a variety of dinosaurs, including hadrosaurs, ceratopsians, and even T-Rex, confirming that at least parts of these animals were covered in this tough, patterned skin. We can tell what time of day some dinosaurs were active by comparing the size of the sclerotic ring, a ring of bone that supports the eye, and the eye socket itself in fossil skulls to those of modern animals. Scientists can infer their activity patterns. The results suggest that large herbivores like Triceratops were likely active both day and night, perhaps to maximize their feeding time. Small predators like Velociraptor were likely nocturnal hunters, using the cover of darkness to their advantage. Large predators like T-Rex, however, don't fit neatly into any category and may have been cathemeral, active in short bursts throughout the day and night whenever hunting opportunities arose. The tails of many dinosaurs were not the droopy, dragging appendages seen in old illustrations. They were held rigidly straight out behind them, counterbalancing the front half of the body. This was made possible by a network of stiffened tendons running along the vertebrae. In dinosaurs like the dromaeosaurs, this made the tail act like a dynamic stabilizer, allowing them to make quick turns and maintain their balance while running at high speeds, much like a cheetah uses its tail today. In the giant sauropods, the tail was a crucial part of their cantilevered bridge-like structure, balancing their incredibly long necks. The sounds of the Mesozoic would have been very different. Alongside the calls of the dinosaurs, the background noise would have been dominated by insects. But there would have been no birdsong as we know it for most of their reign, and importantly, no buzzing of bees or grasshoppers. Grass itself is a relatively recent evolutionary invention and did not exist for the vast majority of the age of dinosaurs. The landscape was dominated by ferns, cycads, and conifers. The first flowering plants and the insects like bees that co-evolved with them only appeared towards the end of the Cretaceous period, changing the world forever. Some dinosaurs had a surprising number of fingers. While T-Rex is famous for having only 2 functional fingers on each tiny hand, other theropods had more. The primitive Herbivores, one of the earliest dinosaurs, had 5 fingers. Allosaurus had 3 powerful clawed fingers on each hand, which were its primary weapons for grappling with prey. The strange herbivorous Therizinosaurus also had 3 fingers, but each was tipped with one of those enormous 3-foot-long claws. The evolution of the dinosaur hand shows a general trend of reduction and specialization over time. Dinosaurs survived one mass extinction, but were wiped out by another. The first was the Triassic-Jurassic extinction event about 201 million years ago. We're not entirely sure what caused it, but it wiped out many of the large amphibians and reptiles that were competing with the early dinosaurs. This event cleared the ecological stage, allowing the dinosaurs to diversify and rise to dominance in the Jurassic period. They were the beneficiaries of one apocalypse, only to be the victims of the next. The KP extinction event, which occurred 66 million years ago, was far more catastrophic. The cause is now almost universally accepted to be the impact of a massive asteroid or comet about 6 to 9 miles, 10 to 15 kilometers wide, which slammed into the Earth in what is now the Yucatan Peninsula in Mexico. This impact created the Chicxulub crater, a massive scar on our planet over 100 miles wide. The evidence for this impact is a thin layer of clay found all over the world in rocks dated to exactly 66 million years ago. This layer is rich in the element iridium, which is rare on Earth's surface but common in asteroids. This was the smoking gun. The immediate effects of the impact were apocalyptic. The impact itself would have released more energy than 1 billion atomic bombs, triggering a massive blast wave, colossal tsunamis, and sending molten rock and superheated dust into the atmosphere. This material would have rained back down, heating the atmosphere to oven-like temperatures and sparking global wildfires. But the worst was yet to come. The dust and soot kicked up into the stratosphere would have shrouded the planet in darkness for months or even years, creating an impact winter. This prolonged darkness caused global temperatures to plummet and, crucially, halted photosynthesis. Plants on land and plankton in the oceans died off on a massive scale. This caused the entire global food web to collapse. The giant herbivorous dinosaurs, deprived of their food source, starved. The carnivores that preyed on them soon followed. It was a chain reaction of extinction that rippled through every ecosystem on the planet. In the end, it's estimated that about 75% of all species on Earth, including all non-avian dinosaurs, were wiped out. But not everything died. Smallness was a key to survival. The creatures that made it through the extinction event tended to be small, under 25 kilograms. Small animals need less food, can reproduce more quickly, and can often hide or burrow to escape the worst of the environmental devastation. Our own ancestors, the small shrew-like mammals of the Cretaceous, survived by hiding in burrows and likely eating insects and decaying matter. When the dust settled, they emerged into a world free of giant dinosaur competitors and predators, an empty world that was theirs for the taking. The extinction of the dinosaurs paved the way for the rise of the mammals, and ultimately for us. The term Jurassic Park is a bit of a misnomer. While some of the dinosaurs featured in the film, like Stegosaurus and Brachiosaurus, were from the Jurassic period, many of the most famous ones, including Tyrannosaurus rex, Velociraptor, and Triceratops, were actually from the Cretaceous period, which came after the Jurassic. They lived tens of millions of years after the Jurassic ended. A more accurate, though less catchy, title would have been Cretaceous Park. Some dinosaurs may have been venomous. The small theropod, Sinornithosaurus, had strange, long, grooved teeth, similar to the teeth of some modern venomous snakes. It also had a pocket in its upper jawbone that could have housed a venom gland. The theory is that it may have used a venomous bite to subdue its prey, which likely consisted of small birds and mammals. While the evidence is not conclusive and is still debated by paleontologists, it opens up the fascinating possibility of another layer of complexity and danger in the Mesozoic world. The longest dinosaur in the world is a trickier question than the heaviest. While Argentinosaurus was the most massive, another contender for the title of longest is Supersaurus. Based on a few key bones, including a massive scapula, shoulder blade, estimates for Supersaurus put its length at around 110 to 140 feet. It was an incredibly long, whip-tailed sauropod from the Jurassic period. Imagine an animal as long as 4 school buses parked end to end. Dinosaur fossils have been found on every continent, a testament to their global dominance. Their remains have been unearthed from the deserts of Mongolia to the plains of North America, from the polar forests of Antarctica to the riverbeds of Africa. Each discovery adds another piece to the puzzle of their long and successful reign, showing how they adapted to and conquered virtually every terrestrial environment on the planet. The first dinosaur to be formally named in a scientific publication was Megalosaurus. Its fragmented bones were discovered in England in the 17th century, but at the time, people didn't know what to make of them. It was initially thought to be the bone of a giant human. It wasn't until 1824 that William Buckland, a geologist at Oxford University, correctly identified it as a giant, extinct reptile and gave it the name Megalosaurus, meaning great lizard. This was nearly 2 decades before the word dinosaur was even invented. The coloration of dinosaur eggs can now be determined. By analyzing the fossilized shells of dinosaur eggs, scientists have found traces of the same pigments that color modern bird eggs. They found evidence of protoporphyrin, which creates reddish-brown colors, and biliverdin, which creates blue-green colors. The eggs of a small bird-like dinosaur called Deinonychus, for example, were likely a pale blue-green color, similar to a modern robin's egg. This suggests that the parents may have nested in open areas and needed to camouflage their eggs from predators, another fascinating behavioral link between non-avian dinosaurs and their bird descendants. There was a dinosaur named after the fictional school of magic, Hogwarts. Dracorex hogwartsia, which means Dragon King of Hogwarts, was a pachycephalosaur with a flat, spiky head that looked remarkably like a mythical dragon. The young visitors at the Children's Museum of Indianapolis, where the fossil is displayed, noted its resemblance to the dragons from the Harry Potter series, and the paleontologists who described it decided to honor that connection in its official name. The brain of a stegosaurus was once thought to be so small that it must have had a second brain in its hips to control its back legs and tail. This theory arose from the discovery of an enlarged cavity in the hip region of its spinal column. However, this idea has since been debunked. This cavity is also found in modern birds and likely housed a glycogen body, an organ whose function isn't fully understood but is thought to be involved in energy storage for the nervous system. It was not a second brain. Stegosaurus managed its massive body with just the one, albeit small, brain in its head. Dinosaurs had a third eye of sorts. Like many modern lizards, snakes, and tuataras, many dinosaurs had a parietal eye, a small opening on the top of their skull that housed a light-sensitive organ. Third eye couldn't see images, but it could detect changes in light and shadow, helping the animal regulate its circadian rhythms, its daily cycle, and perhaps detect predators flying overhead. It's a primitive feature that has been lost in many more advanced animal groups, including mammals and birds. Some dinosaurs were built for digging. A small, strange herbivore called Oryctodromeus, which lived in the Cretaceous period, had adaptations in its snout, shoulder, and hips that suggest it was a powerful burrower. In Montana, paleontologists found the fossilized skeletons of an adult and 2 juvenile Oryctodromeus inside the fossilized remains of their underground den. This is the first clear evidence of a burrowing dinosaur and shows that they had a wider range of behaviors and lifestyles than we previously thought, with some taking refuge from the dangerous world by living beneath it. The question of whether T-Rex was a pack hunter is a subject of intense debate. A trackway site in British Columbia shows 3 tyrannosaurid footprints preserved together, suggesting they were traveling as a group. Additionally, bone beds have been found with the remains of multiple individuals of another tyrannosaur, Albertosaurus, who all seem to have died together. This evidence has led some to propose that tyrannosaurs were social animals that may have hunted in family groups or packs, using their combined strength and intelligence to take down the largest and most dangerous prey. It's a terrifying thought, not just one T-Rex, but a whole family of them working together. The arms of T-Rex, though famously tiny, were surprisingly strong. Biomechanical studies have shown that each arm could likely curl lift over 400 pounds. What they were used for is still a mystery. They were too short to reach its mouth, so they weren't for feeding. Some theories suggest they may have been used to help the animal push itself up from a resting position, or perhaps to grasp onto a mate during courtship, or even to slash at prey that got too close. Despite decades of study, the function of these iconic little arms remains one of paleontology's most popular puzzles. Dinosaurs may have engaged in elaborate mating rituals. The frills of Triceratops, the crests of hadrosaurs, the plates of Stegosaurus, and the feathers of theropods were likely not just for defense or thermoregulation, but also for sexual display. It's easy to imagine a male Parasaurolophus producing a deep, resonant call and flushing its crest with vibrant color to attract a female, or two male Triceratops locking their magnificent horns in a ritualized shoving match to win mating rights. The Mesozoic was likely a very colorful and noisy place during the breeding season. The air sacs in sauropod necks may have been used for display as well. Some sauropods had incredibly long, bifurcated, split, neural spines on their neck vertebrae. It's been proposed that these could have supported large, inflatable air sacs on their necks, which could have been brightly colored and used for visual signaling over long distances, a bit like the throat pouch of a modern frigate bird. It's a speculative but wonderful image, these gentle giants communicating across the plains with giant, colorful neck balloons. The smallest dinosaur eggs ever found are only about an inch long, belonging to a small theropod. This highlights the incredible range of sizes, not just in adult dinosaurs, but throughout their entire life cycle. Every dinosaur, no matter how large, started small. Some dinosaurs had beaks instead of teeth at the front of their mouths. Ceratopsians, like Triceratops, had a sharp, turtle-like beak for snipping off tough vegetation, which was then sliced up by the dental batteries in their cheeks. Many theropods, like the ostrich-like ornithamids and the enigmatic Oviraptorosaurs, also had toothless beaks, which they used for a variety of feeding strategies. The study of dinosaur footprints is a field of science called ichnology. These trace fossils can sometimes tell us more about dinosaur behavior than their body fossils, their bones. A single trackway can reveal the animal's posture, its gait, how fast it was moving, and whether it was traveling alone or in a group. They are a ghost of the animal's life, preserved in stone. The end of the Cretaceous didn't just kill the dinosaurs, it also wiped out the giant marine reptiles like the mosasaurs and plesiosaurs, and the flying pterosaurs. None of these groups were dinosaurs, but they were the dominant rulers of the seas and skies. Their extinction, alongside the dinosaurs, created a massive ecological vacuum that allowed mammals in the sea, whales, and on land, and birds in the air to diversify and flourish. The fastest growing dinosaur was probably the sauropod. To get from a hatchling that could fit in your hand to a 100-ton adult in a few decades required a growth rate that is almost unbelievable. They had the most extreme growth spurt of any animal in history. The dinosaurs with the most teeth were the hadrosaurs. With their complex dental batteries, some species could have over 1,000 teeth packed into their jaws at one time, creating a massive, grinding surface perfect for chewing up the toughest plants. Fossilization is an incredibly rare event. For an animal to become a fossil, its remains need to be buried quickly by sediment, like sand, silt, or volcanic ash, which protects them from scavengers and decay. Then, over millions of years, minerals in the groundwater slowly replace the organic material of the bone, turning it to stone. It's estimated that less than 1% of all living things that have ever existed have become fossils. Every dinosaur bone we find is a lottery ticket that won against astronomical odds. The discovery of soft tissue in dinosaur fossils has revolutionized paleontology. In 2005, Dr. Mary Schweitzer found flexible, transparent blood vessels and red blood cell-like structures inside the fossilized femur of a 68 million-year-old Tyrannosaurus rex. This was thought to be impossible, as organic material was not supposed to be able to survive for millions of years. Her discovery was initially met with skepticism, but has since been replicated. This incredible preservation opens up the possibility of one day being able to study the proteins and other biomolecules of these ancient creatures directly. Some dinosaurs were cannibals. The theropod Majungasaurus from Madagascar is a prime suspect. Paleontologists have found Majungasaurus bones with bite marks on them that perfectly match the teeth of another Majungasaurus. This is some of the strongest evidence for cannibalism in dinosaurs. In a harsh environment, it seems nothing was off the menu. The concept of a Brontosaurus has a complicated history. For a long time, the Brontosaurus was one of the most famous dinosaurs. However, in the early 1900s, paleontologists decided that the original Brontosaurus specimen was actually just an adult version of another dinosaur called Apatosaurus, and the name Brontosaurus was officially retired. For over a century, scientists insisted there was no such thing as a Brontosaurus. But in 2015, a new, exhaustive study of sauropod skeletons concluded that the original Brontosaurus was, in fact, different enough from Apatosaurus to be its own distinct genus. After 100 years in the scientific wilderness, the mighty thunder lizard made a triumphant return. The arms of Dinosaurus were enormous. For 50 years, this dinosaur was known only from a single pair of gigantic, 8-foot-long arms with fearsome claws found in Mongolia. Its name means terrible hand. No one knew what the rest of the animal looked like. It was imagined to be a colossal predator. But in recent years, new skeletons were discovered, revealing the truth. Dinosaurus was ein gigantisch, potbellig, Duckbild Ornithomimosaur mit einem Seil auf seinem Back. Es war eine bizarre, omnivores Kreatur, das justes gigantische Arme und Clowns nicht für Hunden, but likely für Diggen und Gärten Pflanzen. Es ist ein perfektes Beispiel von how neue Discoveries komplett abenden unsere langhilde Annahmen. The dinosaur with the longest neck relative to its body size was probably Mamenchinosaurus. This Chinese sauropod had a neck that could be up to 50 feet long, which was half of its total body length. Its neck had 19 vertebrae, more than any other known dinosaur. How it managed to hold up and control such an incredibly long neck is a biomechanical puzzle that still fascinates scientists. Not all dinosaurs went extinct at the same time. The KPG extinction was a geologically rapid event, but it may have taken thousands of years to play out fully. It's likely that some pockets of dinosaurs in certain parts of the world managed to hang on for a few generations after the initial impact, living in a devastated disaster world before finally succumbing. The popular image of dinosaurs roaring is likely inaccurate. Dinosaurs did not have the larynx or voice box that mammals use to make complex sounds like roars. As the ancestors of birds, it's more likely that they made closed-mouth vocalizations, like the deep hoots, coos, and booms produced by modern birds like ostriches and crocodiles, their closest living relatives. The sound T-Rex made might have been less of a Hollywood roar and more of a deep, terrifying, resonant boom that you would have felt in your chest. Some dinosaurs had feathers on their tails arranged like a fan. The Oviraptorosaurs, for example, had a pygostyle, a fusion of the last few tail vertebrae, just like modern birds, which supports the tail fan. These feathered fans were probably not for flight, but were used for display and for steering and balance, beautiful and complex structures that added to their bird-like appearance. The last of the great dinosaurs were arguably the most spectacular. The final 2 million years of the Cretaceous period in what is now North America saw the evolution of some of the most famous and highly evolved dinosaurs, including Tyrannosaurus rex, Triceratops, Ankylosaurus, and Edmontosaurus. This was the final, glorious flourish of the dinosaur dynasty, an ecosystem populated by some of the largest, most heavily armed, and most powerful creatures of all time, right before the lights went out forever. The study of dinosaurs continues to evolve with new technology. CT scanners allow us to see inside skulls and bones without damaging them. Computer modeling helps us understand how they moved and bit. Chemical analysis of fossils can reveal details about their diet and environment. We are living in a golden age of paleontology, with more discoveries being made now than at any other time in history. Every year, new species are described, and our picture of the Mesozoic world becomes clearer, more complex, and more wonderful. Dinosaurs are the ultimate survivors, in a sense. Their legacy is all around us. They dominated the planet for 180 million years, an almost incomprehensibly long period of success. And while the great non-avian dinosaurs are gone, one branch of their family tree, the birds, survived and thrived. They are a living, flying testament to the resilience and adaptability of the dinosaur lineage. So, the next time you hear a bird sing, remember you are listening to the distant descendant of a creature that once shook the earth. The story of the dinosaurs is not just a tale of extinction. It is a story of incredible success, of breathtaking diversity, and of a legacy that has endured for hundreds of millions of years. A story that is still being written with every new fossil unearthed from the ancient rock. A silent testament to the greatest empire life has ever known. And yet, that empire, for all its grandeur, speaks to us now only in whispers of stone. To hold a dinosaur fossil in your hand is to hold a piece of that lost time, a physical fragment of a world that is almost beyond our comprehension. It is a connection, a tangible link across an unimaginable chasm of 66 million years. The paleontologists who unearth these remains are, in a very real sense, detectives investigating the longest of cold cases. They are not just digging up bones, they are excavating stories. The process is one of infinite patience. It often begins with a glimpse of something out of place, a shard of bone weathering out of a desolate Badlands cliff, a texture in the rock that does not belong. From that single clue, a monumental task unfolds. Brushes and dental picks are used to carefully, painstakingly remove the matrix of surrounding rock, a process that can take weeks, months, or even years for a single large skeleton. Each bone is then encased in a plaster jacket, like a broken limb, for its journey from the field to the laboratory. It is here, in the prep lab, that the true form of the animal begins to emerge, as technicians with the skill of sculptors and the patience of saints free the ancient creature from its stone tomb. This process has a rich and surprisingly dramatic human history, a story of discovery, genius, and bitter rivalry. The late 19th century in North America was dominated by the Bone Wars, a period of intense and ruthless competition between two brilliant paleontologists, Edward Drinker Cope and Othniel Charles Marsh. Their feud was legendary. They spied on each other's dig sites, bribed each other's workers, and even, on occasion, destroyed fossils to prevent them from falling into the other's hands. They rushed to publish descriptions of new species, often making mistakes in their haste, naming the same dinosaur multiple times, or incorrectly assembling skeletons. The famous case of Brontosaurus is a direct result of this frantic competition. Marsh mounted a skeleton of what he called Brontosaurus, but placed the skull of a different dinosaur, Camarasaurus, on top because he hadn't found the correct skull. It was a mistake born of ego and ambition. Yet, for all their animosity and questionable methods, Cope and Marsh's rivalry fueled a golden age of discovery. Together, They named over 130 new species of dinosaur, including some of the most famous we know today, such as Triceratops, Allosaurus, Diplodocus, and Stegosaurus. Their collections form the foundations of some of the world's greatest natural history museums. They were flawed, ambitious men who, in their quest to outdo one another, revealed the scale and wonder of America's prehistoric past to the world. Their battleground was often a place known as the Morrison Formation, a vast expanse of sedimentary rock stretching across the western United States. This geological layer, laid down in the late Jurassic period around 150 million years ago, is one of the richest sources of dinosaur fossils in the world. It represents an ancient environment that was a semi-arid plain, with rivers and floodplains that supported a spectacular ecosystem. This was the world of the true giants. The Morrison Formation is where we find the titans, the long-necked Apatosaurus and Diplodocus, the towering Brachiosaurus, and the heavily plated Stegosaurus. And hunting them all was the apex predator of the Jurassic, the fearsome Allosaurus. Finding these fossils gives us a snapshot of an entire community. We can reconstruct the predator-prey dynamics, the herd structures, and the environment these animals lived in. The Morrison Formation isn't just a graveyard of bones, it's a preserved world, a Jurassic Pompeii that allows us to walk among the giants. Across the globe, another fossil site tells a very different and even more detailed story. The Liaoning province in northeastern China is home to some of the most exquisitely preserved fossils ever found. These deposits, from the early Cretaceous period, were formed in a unique environment of ancient lakes surrounded by active volcanoes. Periodic eruptions would entomb the local wildlife in incredibly fine-grained volcanic ash, preserving them with astonishing detail. It is from the Liaoning deposits that we have found the treasure trove of feathered dinosaurs that proved the link between dinosaurs and birds beyond any doubt. Fossils of creatures like Sinosauropteryx, the first non-avian dinosaur found with evidence of feathers, were covered in a halo of downy filaments. We have found Microraptor with its 4 wings, and the bizarre bat-winged Yi-Chi, which had a membrane of skin stretched between its long fingers. The preservation is so perfect that we can see not only feathers and skin, but also patterns, stomach contents, and sometimes even the chemical signatures of their original color. The Liaoning fossils opened a new window into the Mesozoic, revealing a world of feathered, bird-like dinosaurs that was more vibrant, complex, and strange than we had ever dared to imagine. One of the most spectacular examples of incredible preservation is not a feathered raptor from China, but a heavily armored herbivore from Canada. The Borealopelta Mark Mitchellii fossil, found accidentally by miners in Alberta, is nothing short of a Mesozoic miracle. It is not a skeleton, it is the dinosaur itself turned to stone. This nodosaur, a cousin of Ankylosaurus, was swept out to sea in a flood, sank to the ocean floor, and was quickly buried in sediment in an environment with no oxygen. The result is a 3-dimensional fossil, with its bony armor plates perfectly arranged, its skin and scales intact, and even the keratin sheaths of its horns preserved. We can see its texture, its shape, and, as mentioned, we have even identified its color and its last meal. It is the closest we will ever come to looking at a real, living dinosaur. It looks like it is merely sleeping, not an animal that has been dead for 110 million years. Its existence challenges our very definition of what a fossil can be, a silent, armored ghost from the Cretaceous seas. The internal world of these animals is just as fascinating as their external appearance. Consider the heart of a giant sauropod like Argentinosaurus. To pump blood up its enormous 50-foot neck to its brain, it would have required a heart of immense size and power. Estimates suggest its heart would have been at least the size of an armchair and weighed over 400 pounds. It would have had to generate a blood pressure 6 times higher than that of a human, a pressure that would be instantly lethal to us. The walls of its carotid arteries would have needed to be incredibly thick and reinforced with elastic fibers to withstand this constant, immense pressure. And to prevent the blood from rushing back down and pooling in its legs, its circulatory system would have required a complex series of one-way valves, a system of biological locks to manage the colossal tides of blood flowing through its body. It was a circulatory system operating at the very limits of biological possibility, a cardiovascular engine built on a scale that dwarfs anything on land today. And that blood coursing through those giant arteries would have been red, just like ours. The molecule responsible for carrying oxygen, hemoglobin, is an ancient one, and its iron-based structure that gives blood its red color was well established by the time the dinosaurs evolved. We can even find traces of the original components of these molecules in exceptionally preserved fossils. The discovery of what appear to be red blood cells and collagen fibers inside a T-Rex bone hints that under the right, miraculous conditions, fragments of these ancient proteins can survive across the eons. This allows us to move beyond just bones and into the realm of molecular paleontology, studying the very building blocks of these creatures. It's a field in its infancy, but it holds the promise of answering questions we once thought were permanently lost to time. Questions about their physiology, their relationships, and the very chemistry of their lives. But how did these animals perceive their world? We've talked about sight and smell, but what about hearing? By studying the inner ear structures preserved in their skulls, we can get an idea of the range of sounds they could hear. The long, coiled cochlea of a Tyrannosaurus suggests it was particularly sensitive to low-frequency sounds. This makes perfect sense. The heavy footfalls of its giant herbivore prey, the deep calls of other dinosaurs, these would have been the most important sounds in its environment. It was tuned in to the frequency of giants. In contrast, smaller dinosaurs and the early mammals that lived alongside them had inner ear structures adapted for hearing high-frequency sounds, the rustles in the undergrowth, the chirps of insects, the squeaks of potential prey, or the high-pitched warning calls of predators. The Mesozoic soundscape was divided into channels, with each creature tuned to the slice of the audio spectrum most critical to its survival. The world they walked upon was also in a state of constant, dramatic flux. The late Cretaceous period, the final act of the dinosaurs, was a time of intense geological activity. The continents were continuing their slow drift apart, mountain ranges like the Rockies were being formed, and sea levels were in flux, creating and draining vast inland seaways. It was also a time of massive, sustained volcanic activity. In India, a region known as the Deccan Traps was spewing out colossal amounts of lava and gas, one of the largest volcanic events in Earth's history. For hundreds of thousands of years, eruption after eruption covered an area of over 500,000 square kilometers in molten rock. This would have had a profound impact on the global climate, pumping huge quantities of carbon dioxide and sulfur dioxide into the atmosphere, causing acid rain and wild temperature swings. Some scientists believe that this intense volcanism had already put the world's ecosystems under severe stress, weakening the dinosaurs' reign even before the asteroid delivered the final fatal blow. The end of the age of dinosaurs may have been a 1-2 punch. A planet already sickened by its own internal turmoil, then struck from the heavens. This dynamic planet shaped the evolution of dinosaurs in countless ways. Consider the sauropods of South America versus their cousins in North America. As the continents of Gondwana, the southern landmass, and Laurasia, the northern landmass, drifted apart, their dinosaur populations became isolated. In the south, this led to the evolution of the titanosaurs, the group that includes Argentinosaurus. These were the heavyweights, characterized by their wide-gauge stance, with their legs set far apart like a bulldog's, and often possessing bony armor plates or osteoderms in their skin. In the north, we find the diplodocosids, like Diplodocus and Apatosaurus, and the brachiosaurs. They had a narrower stance and, for the most part, lacked armor. These are subtle but distinct evolutionary paths driven by millions of years of continental isolation, different climates, different predators, and different plants. The family tree of the dinosaurs has branches that stretch across oceans and across continents, a testament to their ability to adapt and thrive in a world whose very ground was shifting beneath their feet. The vegetation of that world was as alien as the animals. Imagine a world without grass. No grassy plains, no savannas, no meadows. For the vast majority of the Mesozoic, the ground cover was dominated by ferns and low-growing cycads. The forests were composed of conifers, ginkgos, and tree ferns. It was a world of greens and browns, a more primitive and stark landscape than the lush, colorful world we know today. The evolution of flowering plants, or angiosperms, in the Cretaceous period was a true revolution. These new, fast-growing plants began to outcompete the traditional gymnosperms. They offered a new, high-energy food source in the form of fruits and flowers, and their rise is closely linked to the success of certain groups of dinosaurs. The hadrosaurs, with their incredible dental batteries, and the ceratopsians, with their slicing beaks, were perfectly adapted to process this tough, fibrous new vegetation. They were the lawnmowers of the Cretaceous, evolving in tandem with this new plant-based fuel source. This co-evolution of plants and plant eaters is a fundamental engine of ecological change, a dynamic that shaped the final chapter of the dinosaur story. Let's delve deeper into the mechanics of their movement. A creature the size of a brachiosaurus, weighing upwards of 50 tons, faced immense structural challenges. Its leg bones were not solid. They were porous but thick and pillar-like to bear the incredible weight. The real magic, however, was in the soft tissues we can't see in fossils. Its feet were likely supported by massive, fibrous, fatty pads like those of a modern elephant, which acted as shock absorbers, cushioning each step and spreading the immense pressure over a wider area. Without these pads, its foot bones would likely have shattered under its own weight. Its ligaments and tendons would have been as thick as steel cables, holding the skeleton together and storing elastic energy with each step, creating a more efficient, bouncing gait that saved precious energy. It was a triumph of biomechanics, a body built not just of bone, but of a complex interplay of cartilage, muscle, and connective tissue, all working in concert to make movement possible on a titanic scale. The social lives of these animals may have been far more complex than we can prove with bones alone. Consider a herd of Triceratops. Fossil bone beds containing the remains of multiple individuals, from young juveniles to old adults, suggest they lived in groups. Within that group, there would have been a hierarchy. Perhaps the dominant males were the ones with the largest horns and frills, their ornamentation a badge of their status. The frill itself, with its unique pattern of hornlets and its rich blood supply, could have been flushed with color to signal mood, aggression, fear, or courtship. Imagine a confrontation between two males, not necessarily a violent, bloody battle, but a ritualized display of power. They would face each other, bob their massive heads, flash the colors on their frills, and perhaps lock horns and shove, a test of strength to establish dominance without risking serious injury. These are the behaviors we can only infer, the rich, detailed life of the herd that the fossils can only hint at. And what about play? We see play in many intelligent, social animals today,
from mammals like dolphins and dogs to birds like crows and parrots. It's a crucial behavior for learning, for practicing skills, and for social bonding. Is it so hard to imagine a young Tyrannosaurus, not yet a fearsome apex predator, pouncing on a log or play fighting with its siblings? Or a group of young hadrosaurs chasing each other in a mock stampede? While we will almost certainly never find a fossil of a dinosaur playing, it is a logical and deeply appealing idea. It helps us to see them not as static monsters, but as dynamic, living creatures with personalities, moods, and an internal life that was likely just as rich as any animal alive today. It breathes life back into the bones and reminds us that these were individuals, each with its own story. The story of their extinction, too, has more nuance than a simple asteroid impact. While the Chicxulub impact was undoubtedly the primary cause, the pattern of extinction was not uniform. In the oceans, the collapse was swift and devastating. The plankton at the base of the food chain died off in the darkness, and everything that depended on them, from small fish to the colossal mosasaurs, starved in a matter of years. On land, the story may have been more drawn out. Freshwater ecosystems seem to have fared better than terrestrial or marine ones. Creatures living in rivers and lakes, like crocodiles, turtles, and fish, had access to a food web based on detritus, the decaying organic matter from the dead forests. This may be why crocodilians survived while their dinosaur cousins perished. They were able to hunker down and ride out the apocalypse by eating the debris of the old world. The survival of the birds is another fascinating chapter in this story. Why did they live when their close dinosaur relatives died? Again, it seems to come down to a few key advantages. The ancestors of modern birds were small, which we know was a key survival trait. They also possessed beaks, which were more versatile tools than the toothed snouts of their relatives. A beak could be used to probe for insects, crack open the newly abundant seeds of the surviving flowering plants, and scavenge for whatever was available. And, of course, they could fly. This gave them immense mobility, allowing them to escape localized environmental devastation and travel vast distances in search of food and habitable areas. They were the ultimate disastrous survivalists, perfectly equipped by chance to inherit a broken world. Reconstructing a dinosaur is an act of both science and art. When a skeleton is incomplete, as they often are, paleontologists must use their knowledge of comparative anatomy to fill in the gaps. They look at the bones of closely related species to infer the shape and size of the missing pieces. This process, called phylogenetic bracketing, is a powerful tool. For instance, if we know that two closely related dinosaurs both had feathers, we can infer that a species that evolved between them likely had feathers too, even if we haven't found direct proof. Once the skeleton is reconstructed, artists and scientists work together to add the muscles, skin, and other soft tissues. They look at the muscle attachment scars on the bones to figure out the size and shape of the muscles. They use skin impressions to determine the texture of the hide. And they look at modern animals in similar ecological niches to make educated guesses about coloration and behavior. Every dinosaur reconstruction you see in a museum or a documentary is a hypothesis, a scientific best guess based on all the available evidence, a beautiful fusion of hard data and informed imagination. And sometimes, that imagination leads us down strange paths that turn out to be true. For decades, sauropods were depicted as swamp-dwelling, amphibious creatures, their necks sticking out of the water like periscopes. The thinking was that they were too massive to support their own weight on land and needed the buoyancy of water to survive. Their nostrils were located high up on their skulls, which seemed to support the idea of them being aquatic snorkelers. This image was ubiquitous in books and movies for 100 years, but a deeper look at the science revealed this was impossible. The water pressure on the chest of a submerged Brachiosaurus would have been so great that it would have been unable to inflate its lungs. Its narrow, elephant-like feet were adapted for walking on firm ground, not slogging through mud. And the trackways they left behind are almost always in terrestrial environments. The high nostrils were likely for another reason, perhaps related to a fleshy resonating chamber or even a small trunk-like structure. The science changed, and our picture of these majestic animals changed with it, moving them from the slow, sluggish swamps onto the dry plains where they truly belonged. The naming of dinosaurs often contains hidden stories. We've mentioned Dracorex hogwartsia, but there are others. Bambiraptor, a small, bird-like dinosaur, was named after the Disney character because of its small size and presumed youth. Gasosaurus was discovered by workers from a gasoline company in China. There is even a dinosaur named Irritator, so called because the paleontologist who described it was incredibly annoyed to find that the fossil dealers who sold him the snout had artificially elongated it with plaster to make it look more impressive. The names are a human fingerprint on this ancient world, reflecting our culture, our language, our sense of humor, and sometimes our frustrations. The sheer number of undiscovered species is staggering. Scientists estimate that we have probably only found a small fraction of all the dinosaur species that ever lived. Many lived in environments that were not conducive to fossilization, like upland forests. Many more lie buried in rocks that are inaccessible to us, deep underground or at the bottom of the sea. New species are being discovered at a rate of about 50 per year, and there is no sign of this slowing down. We are still in the early days of understanding the true diversity of the Mesozoic world. There are entire families, entire ecosystems of dinosaurs still waiting to be found, their stories locked in stone, waiting for the next patient detective to brush away the dust and bring them into the light. Think for a moment about the sounds of that lost world, not just the animals, but the environment itself. The wind would have sounded different rustling through the leaves of ginkgo trees and giant ferns than it does through modern oaks and maples. The storms would have been immense in that greenhouse world, with torrential rains turning the plains into vast, muddy seas. There would have been the crackle of wildfires, far more common in that oxygen-rich atmosphere, and the deep groaning of the earth itself as volcanoes erupted and the continents shifted. It was a world of powerful, elemental forces, a fitting backdrop for the colossal creatures that dominated it. To imagine the Mesozoic is to imagine not just a different cast of characters, but a different stage, a different planet with its own unique sensory palette. The role of disease and parasites in their lives is a field of growing interest. We've found evidence of bone cancer and arthritis, but what about infectious diseases? Coprolites, the fossilized dung, have revealed the eggs of parasitic worms, showing that dinosaurs suffered from internal parasites just like modern animals. Ticks and other blood-sucking insects from the period have been found preserved in amber. It's entirely possible that these insects transmitted diseases. A massive herd of hadrosaurs living in close quarters would have been a perfect breeding ground for epidemics. It's likely that disease was a constant pressure, a powerful force of natural selection that shaped their evolution, weeding out the weak and favoring those with strong immune systems. This is the unseen drama of their lives, the microscopic battles that raged within their colossal bodies. Let's consider the concept of a ghost lineage. This is a lineage in a family tree that is inferred to exist, but for which we have no direct fossil evidence. For example, the ancestors of the great tyrannosaurs of the late Cretaceous must have existed in the early and middle Cretaceous, but for a long time we had found very few of their fossils. They were a ghost lineage. Then, discoveries like Utyrannus and others started to fill in those gaps, giving flesh to the ghosts and showing us the evolutionary steps that led to the ultimate predator. The fossil record is full of these gaps, these missing chapters. Each new discovery is like finding a lost page, helping us to piece together the grand, sprawling narrative of life's history. The very way we see dinosaurs is a reflection of our own time. In the 19th century, they were seen as monstrous, sluggish symbols of an outdated, failed creation, a perfect justification for the Victorian era's belief in progress. In the mid-20th century, they were the lumbering, tail-dragging movie monsters of the Cold War era. The dinosaur renaissance that began in the 1960s, led by paleontologists like John Ostrom and Robert Bakker, reimagined them as active, intelligent, warm-blooded animals, more like birds than lizards. This new vision was a product of a new generation of scientists asking different questions and using new techniques. Today, with discoveries of feathered dinosaurs and soft tissues, we are in another period of revolution, seeing them as even more complex and bird-like than ever before. Our perception of the dinosaurs evolves as our own science and culture evolves. They are a mirror, reflecting our own changing understanding of the natural world. The smallest details can reveal the biggest secrets. A study of the microscopic scratches on the tooth enamel of herbivorous dinosaurs can tell us exactly how they chewed. Diplodocus, for example, had fine parallel scratches, indicating it stripped leaves from branches with a simple forward and back motion. Hadrosaurs, on the other hand, had complex scratches going in multiple directions, revealing the sophisticated grinding motion of their dental batteries. These tiny marks, invisible to the naked eye, open a window onto the precise mechanics of feeding, allowing us to reconstruct the behavior of an animal that has been dead for 150 million years. The sheer scale of their world extended to the insects. During parts of the Mesozoic, high oxygen levels allowed insects and other arthropods to grow to giant sizes. Imagine dragonflies like the Meganeura with wingspans of over 2 feet, or giant millipedes and scorpions scuttling through the undergrowth. This was a world where everything was supersized, a high-energy ecosystem running on supercharged air. The dinosaurs were the rulers of this world, but they shared it with a host of other bizarre and oversized creatures, a supporting cast that made the environment even more alien and dangerous. The end of a sauropod's tail was a formidable weapon. In dinosaurs like Diplodocus and Apatosaurus, the tail tapered to an incredibly long, thin, whip-like section. Biomechanical models have shown that by whipping this tail, they could have broken the sound barrier, creating a deafening crack, like the snap of a bullwhip, but many times louder. This could have been used for communication between herd members, for dominance displays, or as a devastatingly effective defensive weapon against predators. A sonic boom delivered by a 10-ton animal would have been a powerful deterrent to even the most determined Allosaurus. Even their breathing patterns can be inferred from their skeletons. The theropods, like T-Rex, had a system of gastralia, or belly ribs, that were not connected to the spine. These bones would have supported the abdominal muscles, and it's thought they played a key role in breathing, helping to expand and contract the body cavity in a bellows-like motion to pump air through their complex, bird-like respiratory system. This is a level of detail that would have been unimaginable to the first fossil hunters, a deep understanding of their soft tissue anatomy derived entirely from the clues left in their bones. Finally, we must consider the sheer improbability of their existence and of our ability to know them. The chain of events that had to occur is breathtaking. An animal had to live and die in just the right place to be buried and fossilized. The rocks containing it had to survive millions of years of erosion, mountain building, and geological turmoil. Those rocks had to then be exposed on the surface in our time. And then a person had to walk by that exact spot and have the knowledge to recognize what they were seeing. It is a series of near-impossible coincidences. Each fossil is a winning lottery ticket 100 million years in the making. They are gifts from deep time, allowing us a brief, privileged glimpse into a lost world. A world ruled by magnificent creatures that challenge our imagination and expand our understanding of what it means to be alive on this planet. The questions that remain are almost endless. How did they truly communicate? What were the full details of their social structures? How many more spectacular forms are still waiting beneath our feet? The search for these answers continues, a quest driven by the profound and enduring wonder these animals inspire. A fragment of a jawbone found in the desert can rewrite textbooks. A single footprint can change our understanding of behavior, and a speck of preserved pigment can color in a world that has been silent and gray for far too long. This process of coloring in the past often reveals worlds within worlds, ecosystems so strange they almost feel like a different planet entirely. Take, for example, the lost world of Haytag Island. During the late Cretaceous, much of Europe was a series of archipelagos, and one of these islands, located in what is now modern-day Romania, was home to a truly bizarre collection of creatures. For millions of years, a community of dinosaurs lived there in complete isolation, and this isolation had a profound evolutionary effect known as island dwarfism. The giant sauropods, which on the mainland reached lengths of over 60 feet, evolved on Hague into a species called Magiriosaurus, which was no bigger than a horse. The flying pterosaurs, some of which had wingspans of over 30 feet elsewhere in the world, were represented here by Hatzegopteryx. But Hatzegopteryx defied the rule of island dwarfism. It was a monster. With an estimated wingspan of 33 to 36 feet, it was one of the largest flying creatures of all time. But on Hague, with no large theropod dinosaurs to compete with, it evolved into the island's apex predator. Instead of soaring over the oceans hunting for fish, it was a terrestrial stalker, a killer stork the size of a giraffe, with a massive, reinforced neck and a huge, sharp beak, preying on the dwarf dinosaurs that shared its island home. The Haytag Island ecosystem was a funhouse mirror reflection of the mainland, a place where giants became small and flyers became the dominant terrestrial killers. A perfect illustration of how evolution, when given an isolated laboratory, can produce the most unexpected and wonderful results. And while Hatzegopteryx ruled its island, the skies of the wider Mesozoic world were dominated by an incredible diversity of these flying reptiles, the pterosaurs. It is a crucial point to remember that they were not dinosaurs, but a closely related group of archosaurs that evolved flight along a completely separate path. Their wings were not made of feathers like a bird's, but of a leathery membrane of skin and muscle called a patagium, stretched from a single, enormously elongated fourth finger all the way to their ankles. The variety of pterosaurs was astonishing. There were tiny, sparrow-sized parasaurs like Nemicolopopterus that flitted through the prehistoric forests hunting insects. There were filter feeders like Pterodostro, which had over 1,000 long, bristle-like teeth in its lower jaw, forming a sieve that it used to strain plankton and small crustaceans from the water, a prehistoric flamingo. And then there were the giants, the Osdarchids, a group that includes Hatzegopteryx and the even more famous Quetzalcoatlus. These were the largest flying animals in the history of life. Quetzalcoatlus, found in Texas, had a wingspan that could rival a small airplane, easily reaching 33 feet or more. For a long time, it was thought to be a skim feeder, soaring over the oceans and plucking fish from the surface. But its anatomy just doesn't work for that. Like Hatzegopteryx, its long, stiff neck and robust leg bones suggest it was a terrestrial hunter. Imagine this creature, as tall as a giraffe when standing on the ground, stalking through the fern prairies of the late Cretaceous, using its enormous spear-like beak to snatch up small dinosaurs, lizards, and any other animal unfortunate enough to cross its path. The skies of the Mesozoic were not empty. They were a dynamic, dangerous space ruled by these magnificent and often terrifying winged sovereigns. Beneath those skies, the oceans teemed with their own reptilian rulers, equally impressive and certainly not dinosaurs. The seas of the Jurassic were patrolled by two main groups, the Ichthyosaurs and the Plesiosaurs. Ichthyosaurus waren die Speedsters, ein stunning Example von konvergenter Evolution. Dosi wären Reptilien, das evolviert von landdwellenden Ahnenzestern, der Bodies hatten bekommen perfekt streamlined und fish-shaped, almost identisch zu einem modernen Dolphin oder Tuna. Sie hatten eine powervolle Tailfin, Dorsal Fins und Flippers für Steuern. Some fossils are so well preserved, we know they gave birth to live young, tail first, just like a whale, to prevent the baby from drowning. They were the masters of speed, hunting fish and squid in the open ocean. The plesiosaurs, on the other hand, came in two main body plans. There were the long-necked elasmosaurs, the classic Loch Ness monster shape, with a small head on an absurdly long, flexible neck, propelled by four powerful flippers. Their necks could have up to 76 vertebrae, more than any other animal. They were likely ambush predators, using their long necks to dart their heads into schools of fish. Then there were the pliosaurs, the short-necked plesiosaurs. These were the apex predators of the Jurassic seas. Creatures like Liopleurodon and Kronosaurus were underwater titans with huge skulls filled with dagger-like teeth. They were the ocean's equivalent of T-Rex, hunting ichthyosaurs, large fish, and even other plesiosaurs. By the Cretaceous period, however, a new dynasty of marine predators had risen to dominance, the mosasaurs. These were not related to plesiosaurs or ichthyosaurs, but were essentially giant aquatic lizards, most closely related to modern monitor lizards. They were latecomers to the scene, evolving in the last 20 million years of the Cretaceous, but they diversified rapidly and took over the oceans. Mosasaurs had long, serpentine bodies, powerful flippers, and a strong, flattened tail for propulsion. The largest of them, like Mosasaurus hoffmanni, could reach lengths of over 50 feet, making them some of the largest marine predators of all time. Their skulls were doubly hinged, like a snake's, allowing them to open their mouths incredibly wide and swallow huge prey whole. They even had a second set of teeth, called pterygoid teeth, on their palate to help grip struggling prey and drag it down their throat. Fossil stomach contents show they ate anything they could catch: giant fish, ammonites, sea turtles, plesiosaurs, and even seabirds and pterosaurs they snatched from the surface. For the final stretch of the age of dinosaurs, if you went for a swim in the ocean, you were no longer at the top of the food chain. The mosasaurs were the undisputed, terrifying rulers of the Cretaceous seas. Back on land, the life of any dinosaur, from the smallest herbivore to the largest predator, was a story of dramatic transformation. The study of this growth from hatchling to adult is called ontology, and it reveals that young dinosaurs often looked and behaved very differently from their parents. Perhaps the most extreme example is Tyrannosaurus rex. For decades, paleontologists kept finding fossils of a small, slender, long-legged tyrannosaur that they named Nanotyrannus, the dwarf tyrant. But a growing body of evidence now suggests that Nanotyrannus was never a separate species at all. It was simply a juvenile T-Rex. A young T-Rex was a very different animal from its bone-crushing parent. It was built for speed and agility, with long legs, a lightweight frame, and blade-like teeth suited for slicing, not crushing. It occupied a completely different ecological niche, likely hunting the smaller, faster dinosaurs that the hulking adults were too slow to catch. As the T-Rex grew older, it underwent a profound metamorphosis. Its skull became deeper and more massive, its teeth grew thicker and more robust, and its body became bulkier, trading speed for raw power. This change was so dramatic that it was like two different species living in the same environment. This ontogenetic shift meant that tyrannosaurs didn't have to compete with their own young for food. The teenagers hunted the medium-sized prey, while the adults took on the giant, armored Triceratops and Edmontorosaurus. The species effectively dominated multiple predatory niches at once, which may have been a key factor in its incredible success as the ultimate apex predator. This radical change in appearance throughout a dinosaur's life presents a huge challenge for paleontologists and the artists who bring their work to life. The problem of shrink wrapping is a constant debate in paleoart. This is the tendency to draw dinosaurs with their skin stretched tightly over their skeletons, making every bone and muscle visible, as if the animal had zero body fat. In reality, living animals have layers of fat, loose skin, and other soft tissues that completely change their silhouette. A lion is a powerhouse of muscle, but you don't see every sinew. You see a thick, furred creature. A hipposkeleton gives little hint of its massive, barrel-shaped body. Dinosaurs would have been no different. They would have had fat reserves to survive lean times, thick neck muscles, and perhaps even dewlaps, wattles, or other soft tissue display structures that we have no fossil evidence for. The heavily armored Borealopelta, for all its spiky glory, was found to have a thick layer of subcutaneous fat beneath its armor. Modern reconstructions are starting to move away from the shrink-wrapped look, giving dinosaurs more plausible bulk and heft, depicting them as real, fleshy animals rather than just animated skeletons. This includes adding speculative features based on modern analogs, like porcupine-like quills on a Psittacosaurus or the inflatable throat sacs on a sauropod. It's a move toward portraying these creatures not just with anatomical accuracy, but with biological plausibility. This challenge extends to every aspect of their biology. Consider their sleep patterns. Did dinosaurs sleep? Of course they did. Every complex animal needs to rest. But how did they do it? Did a giant sauropod lie down, a process that would have been a monumental effort? Or did it sleep standing up, like a modern elephant or horse? Did theropods curl up? We have a stunning fossil from China of a small feathered troodontid named Mei Long, which means soundly sleeping dragon. This fossil is preserved in a perfect three-dimensional sleeping posture. It is curled in a tight circle, its head tucked under its arm, in a position identical to that of a sleeping bird. This posture, known as roosting, is used by modern birds to conserve body heat. Finding a non-avian dinosaur in this exact same pose is one of the most beautiful and compelling pieces of evidence linking them to birds. It's a quiet, intimate moment, a peaceful behavior frozen for 125 million years, a snapshot that reveals more about the living animal than 1,000 scattered bones ever could. It allows us to imagine a prehistoric night, not filled with constant roaring and fighting, but with the quiet, rhythmic breathing of countless sleeping dinosaurs tucked in against the ancient cold. Even their brains, the source of their behaviors, are no longer complete black boxes. While the soft tissue of the brain is never preserved, the inside of the skull cavity, the endocranium, is a perfect mold of its shape. Using high-resolution CT scans, scientists can create detailed 3D digital models, or endocasts, of dinosaur brains. These models reveal the size and shape of the different lobes. We can see a large cerebellum, the part of the brain that controls motor skills and balance, which is exactly what you'd expect in a dynamic, bipedal animal like a theropod. The cerebrum, associated with higher cognitive functions, is larger in dromaeosaurs than in a stegosaurus, confirming our suspicions about their relative intelligence. We can even trace the paths of cranial nerves and major blood vessels, giving us clues about the power of their senses. In T-Rex, the optic nerves were massive, suggesting it had excellent vision, and the huge olfactory bulbs confirm its profound sense of smell. The inner ear's semicircular canals, which control balance, can be mapped to understand how it held its head and how agile it was. We are, in essence, reverse engineering their neurology from the empty spaces they left behind, building a picture not just of their bodies, but of their minds and their unique sensory experience of a lost world. That sensory experience would have been shaped by an environment that was often far from benign. The Mesozoic world was not a stable paradise. It was a world of extreme weather, including massive hurricane-like storms. Recent research into the geology of the period suggests the warmer global climate and higher sea levels could have fueled storms of an intensity we can barely imagine today, so-called hypercanes. These storms would have wreaked havoc on coastal ecosystems, destroying nesting grounds, defoliating forests, and causing massive floods that could drown even the largest dinosaurs. A bone bed in Alberta, Canada, containing the remains of hundreds of Centrosaurus, a horned dinosaur, is thought to be the result of a single herd trying to cross a river swollen by a massive coastal storm. They were all drowned together, a catastrophic event that became a paleontological treasure. These were not just animals living in a static landscape. They were constantly battling the elements, their lives shaped by drought, fire, flood, and storm, forces of nature that were every bit as dangerous as the predators they feared. And amongst all this grandeur and danger, there were the unsung inhabitants of the Mesozoic, the creatures that lived between the footfalls of the giants. The undergrowth teemed with a diversity of life that we are only just beginning to appreciate. There were early mammals, most of them small, nocturnal, shrew-like creatures, living in burrows and surviving on insects and seeds. But some were more specialized. There was Repenomamus, a badger-sized mammal from the Liaoning deposits, whose fossil was found with the bones of a baby Psittacosaurus in its stomach. Direct proof that at least some Mesozoic mammals hunted small dinosaurs. There was Castoracota, a beaver-like mammal with a flattened tail and webbed feet, adapted for a semi-aquatic life. And there was Volaticotherium, a gliding mammal with a skin membrane that allowed it to soar from tree to tree, a prehistoric flying squirrel. The world of the dinosaurs was not just a dinosaur world. It was a complex tapestry of life, with lizards, snakes, frogs, salamanders, turtles, crocodiles, and these surprisingly diverse mammals all playing their part in the ecosystem, their stories unfolding in the shadows of their giant reptilian overlords. This complexity makes piecing together the true picture of their world an ever-evolving puzzle. A common misconception is that paleontology is mostly about digging. In truth, a huge amount of the work is done in the lab and on the computer. Bone histology, the microscopic study of bone structure, is a field that has unlocked incredible secrets. By cutting a paper-thin slice from a fossil and examining it under polarized light, we can see the very fabric of the bone. We can see the density of blood vessels, confirming the high metabolisms of many species. We can see lines of arrested growth, or lags, which are like tree rings that mark seasonal changes, such as a dry season when food was scarce and growth slowed down. By counting these lags, we can determine the precise age of an individual dinosaur when it died. It's how we know that Sue the T-Rex was about 28 years old. This technique allows us to build growth curves for different species, to understand their life histories, how quickly they reached sexual maturity, and what their average lifespan was. It's like reading the autobiography of an animal written in the language of its own bones. Another powerful tool is stable isotope analysis. The chemical elements in an animal's bones and teeth, like carbon, oxygen, and strontium, come from the food it eats and the water it drinks. The isotopic signatures of these elements vary from place to place and between different types of plants. By analyzing the isotopic ratios in a dinosaur's tooth enamel, scientists can determine what it was eating and even where it was living. Strontium isotopes, for example, are a geological fingerprint. By comparing the strontium in a dinosaur's tooth to the strontium in the surrounding rocks, we can tell if that animal was local or if it had migrated from a different region. Studies on hadrosaurs have used this technique to show that they undertook long seasonal migrations, traveling hundreds of kilometers, likely to follow the growth of vegetation or to reach specific nesting grounds. This transforms them from static museum mounts into dynamic, migrating animals, their lives governed by the changing seasons on a continental scale. The very air they breathed, captured in tiny bubbles in ancient amber, tells a story as well. Analysis of this fossilized tree resin has confirmed that for much of the Cretaceous, atmospheric oxygen levels were significantly higher than today, perhaps as high as 35%. This oxygen-rich environment would have had profound implications. It would not only have fueled their high-energy metabolisms and allowed for giantism, but it would have also made the world incredibly flammable. Wildfires would have been far more frequent and far more intense. Many ecosystems may have been fire-adapted, with plants that required fire to release their seeds, much like some pine forests today. Dinosaurs would have had to contend with these infernos as a regular part of their lives. It paints a picture of a world that was not only full of giant predators, but was also periodically scoured by immense walls of flame, a volatile and dangerous crucible that forged some of the most resilient creatures in Earth's history. The very atmosphere was a source of both life-giving energy and catastrophic destruction. As we continue to explore, we find their influence even in the rocks themselves. The great dinosaur track sites are not just collections of individual footprints. They are records of ancient landscapes being physically altered by the passage of these animals. In some locations in Colorado, the ground is so heavily trampled by the feet of giant sauropods that the layers of sediment are completely mixed up and churned, a phenomenon known as dinoturbation. These animals were geological forces in their own right. A large herd of sauropods moving through an area would have been like a fleet of living bulldozers, clearing paths through forests, compacting the soil, and altering the flow of rivers. Their immense size and numbers meant they were not just living in their environment. They were actively engineering it, creating and maintaining open spaces that allowed for different types of plants to grow, which in turn supported other species of animals. Their impact was written into the very stone of the planet, a physical legacy of their long and heavy-footed reign. What's truly humbling is the realization that this vast, complex world, which lasted for 180 million years, is a story that we have only just begun to read. The number of paleontologists in the world is smaller than the number of people who work in a single large office building. The areas of the globe that have been thoroughly explored for fossils are tiny compared to the vast expanses that remain untouched. There are almost certainly entire faunas of dinosaurs, ecosystems as unique and strange as Haight Island, that are still completely unknown to us, their bones lying in silence in the rocks of the Amazon basin, the Siberian wilderness, or beneath the Antarctic ice. The golden age of discovery is far from over. In many ways, it is just beginning. Every field season brings the potential for a new discovery that could once again revolutionize our understanding. A bone that could topple a long-held theory, or a feather that could add a new splash of color to our ever-sharpening picture of the past. The narrative of the dinosaurs is not a closed book, but a library with countless volumes still waiting to be opened.
Their world is not just a subject of historical study, it is a frontier of active exploration, pushing the boundaries of technology and human curiosity.
We continue to look back, not just out of a sense of wonder for what was lost, but because understanding the greatest dynasty in the history of life provides a crucial context for our own fleeting moment on this planet. The deeper we dig, the more we realize that their world was more intricate, more dynamic, and more bizarrely wonderful than we ever could have conceived.
It was a world where evolution ran wild, producing creatures of every shape and size, filling every conceivable niche on a planet that was itself constantly changing, a grand and epic drama played out over a timescale that defies human comprehension. And within that drama, countless smaller stories played out, lives of struggle, survival, and surprising tenderness.